we'll have a month break and restart later in August. But we're very happy to have Wlodek Bryc from Cincinnati. So he'll be talking about fluctuations of the height function for open ASEP. So Wlodek, please start.
Thank you very much for the invitation. It is a pleasure to be in Brazil, even if it is only remotely. I guess for this audience, I don't have to expand the acronym, but I realized after I wrote the abstract that I never mentioned that this is called Asymmetric Simple Exclusion Process. And this is based on work with several people and more than one work. There are various combinations of those people that we worked on various parts of this project. So my plan is, I never know what will be the audience, so I think I want to say a few words about open ASEP and about height function, which perhaps I shouldn't. Should I skip that? Oh, you are muted.
Sorry, yeah, please go through as you plan.
So that's one other thing, that is, if you have any comments and questions, please unmute yourself and ask, because if you say type them in the chat, then I think I will not even see them because of the way I have my presentation arranged, the system arranged. So then I want to say the main thing, the theorems about fluctuations of the height function, and depending on time, I will say something about method of proof, maybe close to nothing. We'll see. So the first thing that I want to say is that asymmetric simple exclusion process is actually a bunch of different models that are closely related but different. And the open ASEP is actually the oldest of them. So this is a model that comes from a paper in biology. Okay, let's call it biology, by Catherine MacDonald, Julian Gibbs, and Alan Pipkin. As you know, in biology, the authorship is not alphabetical, so the mathematician in that group is Alan Pipkin at the end. So what they did is they proposed a model of a Markov process for whatever biological phenomenon they had, and the model had 6 parameters, of which one I sort of eat into time. So I call them 5 parameters, alpha, beta, that are positive, gamma, delta, that I think they had also been positive, and Q, which is between 0 and 1. They had one other parameter, which they called L, which for the ASEP, L is 1. But for their model, they said the empirical evidence for the model is actually L is 27. What is L? L is how far apart the particles must stay. And in the ASEP, they can be next to each other, so the distance 1. So basically, the model is, sorry about that. So the model is that you have a bunch of sites that are either occupied or empty, and I sort of mark them as circles. And then the particles can arrive at the rate alpha, or leave at rate gamma from the left endpoint. And of course, the particles cannot arrive if the site is busy. That's the exclusion part of the process. Once the particle is in the system, it can go right, or it can go left. So this is the 2 parameters that MacDonald and others had. I eat one of the parameters into time, so I speed up time so that this rate is 1, and the other one is less than 1. And so the word simple is that you go to the nearest neighbors. The exclusion I already mentioned. Asymmetric is the Q. Q is not allowed to be 1. Q can be 0, though, in which case you have a motion from the left, especially if you take Q equals 0, gamma and delta 0, then you just have the movement from the left reservoir to the right reservoir. And the right reservoir is, again, you can have, if a particle is at the endpoint, then it can leave at a rate beta. And there is some, you can allow also for the chance of the particle arriving from the reservoir at some rate. So that's the model that they were interested in. The number of sites, which is n here, In genetics, this is the length of the gene. So it is, thousands of locations. So this is large number. So the next thing that I want to do is I want to say about the height function. So if you have a Markov process, this is an informal description of the evolution of a Markov process. Particles arrive from the left, particles arrive from the left. I think you can see this cursor from the left, and then they jump around. If they can, the particles next to each other cannot jump into the occupied sites, and then they leave. And instead of describing this configuration as the as a picture, one can write down the height function. So essentially what you do is the height function people do differently sometimes. And what I'm doing is I'm sort of, for a height function, I'm marking argument x between 0 and 1. So the location of the first particle is 1 over n. And then what you do is you go one step up if the particle is there, one step down if the particle isn't there, one step up, one step up. As you can see, I have a cheat sheet here, one step down, so that I don't make mistakes, one step down, one step up, one step down, one step up, one step down. And then when you have this, then the height function h n of xt is equally good description of the state of the Markov process. And you can talk about evolution of such a curve as a Markov evolution. There is an interesting thing to point out is the endpoint behavior. The endpoint, the beginning of the curve is, if the particle that was here leaves, then, well, the height function would have to be like this. It would have to go down. So essentially if the particle leaves, you would have to move the endpoint 2 units up. And of course, if the particle wasn't there and it arrives at the endpoint, then you have to move 2 points down. And that's why there is this technical definition that hn of 0t is minus twice the net flow of particles from the left up to time t. And then the rest of the height function is, I wrote this as a stepwise function, not as a continuous. Continuous is easier to draw, but for formula, it is easier to write down the step function. That is, you go up or you go down depending on the value of the process. The value of the process is 0 or 1. That is, for each location, the value of the tau is 0 or 1, and it of course depends on time. So what is still not known for open ASEP is the behavior of hn0 of t. That is, people know when t goes to infinity and maybe when n goes to infinity, and people know that the behavior is roughly going to minus infinity, and there is a rate that for some choices of parameters, people know that there is another n here, I think, and the constant times t times square root of n. But the interesting part is really the fluctuations. In some other models of ASEP, the fluctuations are related to important statistics like GUE things. But for this one, nobody knows. On the other hand, if you look at the second part of this height function, then this is the difference between hn of x of t and hn of 0. And this is just a partial sum of the values of the Markov process. And the Markov process is in the finite state space, 2 to the n values. So it converges in the law. And therefore, you have this, what I call the height function hn of x. You have this limit as t goes to infinity. And this is what I will be interested in. That is, I will be interested in the fluctuations of this. I don't know if I should call it height function. I would like to say height function, but you can also say that sort of describes particle density, number of particles up to location x. So this is what I will be interested in. And of course, I will be starting the process from stationary distribution. So basically, I'll be looking at this hn of x as plus minus ones, depending on whether tau j is plus or minus 1. And tau j's will have the law that is the stationary distribution of open ASEP. This is the law that depends on, well, 5 parameters. Finding the law of open ASEP is not exactly a trivial task. if you have patience, you can write down the formula, use software to compute the values for small n. I did it for n equal 2 and n equal 3. So you have 4 by 4 and 8 by 8 matrix to work with for the transition intensities. And what you get from Mathematica is something that one cannot make any sense of. There is a recursion on n, which comes from a paper by Liggett from 1975, which tells you how to compute the probability, stationary probabilities for one n if you know them for the previous n. And then there is this ingenious method of Derrida, I should probably point out here, Derrida, Evans, Hakim, and Pasquier. And the method consists of, I'm not saying why, but the method consists of finding a pair of typically infinite matrices D and E, which satisfy this Q commutation equation, dE minus QED is D plus E, and then finding two vectors W, which is the left eigenvector of the matrix linear combination of E and D with eigenvalue 1, and finding the vector V, which is the right eigenvector with eigenvalue 1 of a linear combination of matrices D and E. The coefficients of the linear combination of vector W are the coefficients that you use on the left end of the process for the reservoir from which things come. And for V, the coefficients are describing the movement to the right. And then if you want to compute, for example, probability of the sequence 0, 1, 1, 0, 1, stationary probability, then what you need to do is you need to take those matrices. E is for empty, D is, I suppose, for occupied. So D codes for ones and E codes for empty, and you write them down in this sequence, multiply them out, apply the vector from the left, apply the vector from the right, you get a number. And if you do it for all the linear combination, for all the 2 to the n sequences, then you got the probabilities, you just have to normalize them. And this is, I sort of wrote down the normalization as well. So this is the ingenious method that people in physics came up with. There is a misconception that this method encodes recursion of Liggett. In fact, it is not. In fact, you just prove it from Kolmogorov's relations, or Kolmogorov differential equations, and verify that everything is 0 by. So before I can talk about fluctuations, I have to talk about the law of large numbers. So there is this phase diagram for ASEP that was discovered actually early on. That is, people in biology discovered this, that the behavior of the system, at least large size system, differs depending on the choices of parameters. That is, there are 3 regions in the space of parameters. Well, 3 regions that, the space of parameters is 5-dimensional. So it is somewhat amazing that you can just draw the picture. And the way you draw the picture is that you encode the parameters alpha and gamma, the one from the left end of the ASEP, in terms of 2 other parameters, C and D. This is the relation how you compute alpha in terms of C, but of course you can compute C in terms of alpha and gamma, and that's a quadratic equation. The quadratic equation has 2 solutions, and those are C and D, and the convention that I chose is that C is positive. So of the 2 roots, one is positive, and the C denotes the positive root. And then you do the same thing with the other endpoint, and it's really the same equations. And you solve quadratic equations, and A is the positive parameter. And it is somewhat miraculous that those 2 parameters, A and C, is what determines the law of the large. Maybe it is not miraculous for people in physics. Maybe it is not miraculous for people in biology, but to me it was miraculous that those 2 parameters describe all the complications that happen in this Markov process with 5 parameters. So basically what happens is you have a low density region where if C is bigger than 1, then what happens is really alpha is small. If C is big, then alpha is small. If alpha is small, you don't have enough particles coming in, so you don't have many particles in the system. And that is reflected by the law of large numbers. This is actually a local law of large numbers. That is, if you do this sum from J equal A, if you do this sum up to, say, maybe I should say it, if you do this sum up to n times x instead of up to n, then you get x here. In other words, this is local density of particle density, as sometimes people say in physics. The particle density in the system is less than 1/2, 1 over 1 plus c. If the parameter a is large, which means beta is small. Now this is the problem with this new revision, which means if A is large, then beta is small. If beta is small, not many particles leave the system. And therefore, what you get is you get congestion. So this is high density phase. And this is expressed by the fact that the law of large numbers gives you the average number of particles per site, A over 1 plus A, which happens to be bigger than 1/2. And the region that, A and C are between 0 and 1 is called the maximal current region, because not only that the average number of sites occupied is 1/2, but also the flow through each of those bonds, the average flow through those bonds is maximal. So you would think that this biology system of McDonald would be operating in that regime, that things would try to run as efficiently as possible. So I think I'm ready to say something about the fluctuations. So the height function that I have is, if you divide this height function by n, then the height function divided by n goes to 0 if your parameters are in the interval 0, 1. So if you're in this maximal current phase. And then the natural thing to do is to say, if you have a lot of large numbers, then maybe you want to have the central limit theorem. So this is what this normalization is. You take 1 over square root of n times the sum of the values of the plus minus 1 valued random variables up to nx, and you ask to what process this converges. And the amazing thing discovered by Derrida, Enaud, and Lebowitz in 2004 is that this converges to the sum of 2 independent processes. One of them is something that everybody would expect. You would expect Gaussian limits in the central limit theorem, but the other one is not. The other one is Brownian excursion, which you may think about as a positive Brownian bridge. So in other words, when x is 1, then you do have central limit theorem, because b at 1 is 0. But when x is 1/2, you get Brownian motion plus something positive, random independent positive. Now, the method of proof in that paper was the matrix method, and the matrix method makes it easier to work with as many parameters as you can think of being 0, because then the matrices are easier, simpler to work with them. So they worked with q equals 0. Maybe I should highlight it forever. And then they doesn't want to highlight this forever. So they worked with q equals 0, and they also worked with b and d equals 0, which corresponds to gamma and delta being 0. Really. Still, it's a very interesting result. And there is a sentence in the paper that says, we believe that our results also hold for the general ASEP, where the particles can also jump to the left with a rate q smaller than 1. So this is clearly asking for somebody to prove it, but it is not a very surprising thing to get. I'm not sure whether they also meant to say that B and D, what to do about B and D, that I don't know. Whether they also meant that you should allow gamma and delta non-zero, but we'll see in a moment. I want to also point out that, well, q smaller than 1, then sure, something is true for q equals 0. Why wouldn't it be true for q equals smaller than 1? But there is this case q equal 1 that was worked out by also Derrida and Landim. And the fluctuations there, you have to do the correction. So essentially what I did, I took my hn of x and added back 1 to cancel this and subtracted the average that is now depends on the location. So now the average is not, particle density is not constant. And but once you subtract the law of large numbers and then normalize by 1 over square root of n, then for Q equal 1, you get Gaussian fluctuations. The Gaussian, which is not Brownian motion, is much more complicated. Nevertheless, you do get Gaussian fluctuations. And also, this is somewhat stable. That is, if you say, how about Q varying with N and converging to 1, then you also get Gaussian fluctuations. So the question, do you believe that Q smaller than 1 should be true? Well, this is, one can think, yes, they are right, but are they, I think it's worth checking. So this is what we did with Yizao. So we have a paper with Yizao from 2019, where we sort of, extended this result of Derrida and Aoud and Lebowitz to Q smaller than 1, and also to allowing gamma and delta less or equal than 0. So essentially what we showed is that if you take the fluctuations and center them like they did, then you do get a Brownian motion plus another process, which are two independent processes. And this process X is a Brownian excursion if A and C are in the interval 0, 1. So it's sort of extending, confirming their belief, let's put it this way. But there were some other things that we worked out by the same technique that we sort of developed for this process. And you shouldn't read the rest of the things, because I will have a phase diagram where I will show the same thing on the phase diagram, and I think that's more legible. So what we did is we confirmed the case that Derrida Lebowitz and Aoud Lebowitz did. So this is, in this case, when A and C are between 0 and 1, then you get Brownian motion plus Brownian excursion. Let's look for a moment at the hyperbola AC equal 1. When AC equals 1, everybody knows what happens. When AC equals 1, then the invariant measure of the open ASEP, so this is choosing parameters alpha, beta, gamma, delta correctly, so that A times C comes up to be 1. Then the stationary measure of ASEP is just Bernoulli measure. It is actually Bernoulli with probability 1/2 at the tip, at the A and C equal 1, but it's always Bernoulli for A times C equal 1, Bernoulli with this probability here, A over 1 plus A. And of course, in this moment, you clearly say, well, we know what are the fluctuations of this. The fluctuations are normal, the Brownian motion, with the correct variance, because you don't have variance, you have to choose the variance. Now you have to change the normalization, which is what I did here. That is, I said, instead of taking 2 tau j minus 1, I now take 2 tau j minus whatever the limit is, which is A over 1 plus A if IA is bigger than 1, and 1 over 1 plus C if C is bigger than 1, and 1/2 in this region that I already marked, the maximal current region. So what is not difficult to work out is what happens also if you keep this A fixed and you change the C. So if you go through this region up to AC equal 1, then you get the same standard correction, Brownian motion with a variance corrected variance, and you do use the same standardization. So you subtract minus 2 rho throughout. And of course, symmetrically, if you choose a point on the parabola A times C equals 1 and now vary A, then you also get Brownian motion with a correction of the variance. I don't know what's your feeling about this part. We don't know because our technique, the technique that we use does not allow us to cross the line A times C equal 1. So we have no access to this. But if you say, how about this point? Well, maybe everywhere everything is Gaussian, but the normalization at this point is inconsistent if you just stick with the same normalization that worked below the AC equal 1 line. So this is the mystery. But then here is another, I don't know if you call it mystery or not. What happens if, so here we have Gaussian limit, everywhere here we have Gaussian limit. And here we have Brownian motion plus excursion. So what happens at the boundary? Well, what happens at the boundary is that you get Brownian motion plus Brownian meander. So a process that is a Brownian motion condition to stay positive. And somewhat similar, you get the dual result on the other boundary. There is a particle-Hall duality that sort of switches the roles of A and C. So basically, that's what we worked out in that paper that I mentioned. We worked out what happens in the low density and high density regions, but below the line AC equals 1. And we worked out what happens when A is 1 and C is not smaller than 1, or C is 1 and A is smaller than 1. And then we confirmed the belief of Derrida and Auden and Lebowitz that within the maximal current range, we have the result as they believe, the Brownian motion plus Brownian excursion. So the next question is, the most interesting point perhaps here is this point here, where maybe I should use this marker. This point here, which is sometimes called the triple point, and from our point of view, it's actually 1, 2, 3, 4 quintuple point, because this is where the three main regions meet: low density, high density, low density, high density, and maximal current. But it's also the point where we sort of cannot cross this line. So it is interesting to ask what happens if. So we know what happens exactly when A is 1 and C equals 1. We just have the height function, the fluctuations of height function are Brownian motion. But what happens if you, change the value of A with the system size and approach A and C and approach point 0.11 from this region, from the Gaussian region, or from the multiple current, maximal current region, so where the Brownian excursion governs the fluctuations, or from this region? Well, it would be interesting to know what happens if you approach this from this direction or this direction, but those we cannot touch for technical reasons. We can only say what happens if you follow the tangent line. And if you follow the tangent line, the fluctuations are Gaussian. So it's sort of, that's a quick answer. So this was worked out in two settings. One setting was worked out by Corwin and Kuznetsov. This is the date on the archive paper, where in addition to choosing this A going to 1 at a rate A or some of roughly of the square root of n with a parameter, and C going to 1 with the rate C over square root of n. In addition, they took Q going to 1 at a very specific rate. And then B and D were matched, and that's important in their proof, were matched with Q. So they are minus Q, and they are going to the maximal lower. So B and D, for every value of B and D, the values are restricted to be always bigger than -1, but then minus Q, and they go to the boundary. And then we have also a preprint with Yizao, Wang, and Jacek Wesolowski, where we did the same problem for fixed Q. So here is a paper of Corwin and Kuznetsov, but you can see that I have all sorts of other papers listed here. So basically, there's a paper of Corwin and Shen about what happens to height function in this regime when you take the height function of the ASEP, the full height function with t, with time, in this regime where Q goes to 1 and A goes to 1, A and Bn goes to 1, and this regime that I described above. And what happens is that the height function converges to the solution of the KPZ equation with Neumann boundary conditions, and the boundary conditions are related to those parameters A and C. So that's the paper of Corwin and Shen. And then Corwin and Kniesel decided to use this to determine the stationary, what they call stationary measures of the KPZ equation. And this they reach by looking at the stationary part of the height function for the ASEP with varying parameters, which is exactly this height function that I have here. So essentially analyze the fluctuations of this height function that I was talking about all the time. And what they show is they actually determine the multiple point Laplace transform of Hn of x, and therefore they determine in some sense uniquely the stationary measure, but it is a complicated expression that is difficult to know what really it is. And it turns out that the answer is, again, 1 over square root of 2 of the Brownian motion. That part can be read out, obviously, from the Laplace transform, because you know what's the Laplace transform, plus another process which is independent of the Brownian motion. And this other process is something that was sort of worked out in two papers differently by Bryc and Ledoussal. So this paper already appeared, and another paper with Alexey Kuznetsov, Yizao, Wang, and Jacek Wesolowski. Those two papers, the preprints appeared like within a week of each other, and we happen to be the first, but really, you know, it's random. So the description that I'm giving here is actually from Bryc and Ledoussal paper. In some sense, the description is more robust. So they describe process X in the following way. They say the process X has continuous trajectories, and furthermore, its distribution is absolutely continuous with respect to the Brownian motion of variance 1/2. So, you know, it's this 1 over square root of 2bx. That's the Brownian motion of variance 1/2. And the Radon-Nikodym derivative is given by this formula with e to the minus ab1. This part is really just the drift, if there were none. And then there is this integral from 0 to 1 of e to the minus the process, and then raised to the power negative a plus c over 2. So the first thing that I want to point out, and I can see it here, is that if a plus c is 0, then there is no integral, and then you get just the Brownian motion with drift. And that thing, of course, Corwin and Kniesel knew as well. So it's sort of confirming that this answer matches the cases that are known. The other interesting thing is that there is a paper of Haria and Yor from 2004 about this kind of processes with a Radon-Nikodym derivative given in this form, except that instead of the interval 0, 1, they consider interval 0, L. And it turns out that the answer here is something that people in financial mathematics were interested in and considered before. So that's somewhat surprising thing. So in fact, both Bryc and Ledoussal and also in our paper, it was more convenient to choose the interval 0L rather than the interval 0,1. And it is not 100% clear whether this interval 0L corresponds to the KPZ equation on the interval 0L. Probably it does, but it requires requires some time to check those things, and everybody is busy with checking new things instead of old things. So the process that Bryc and Ledoussal considered, I put parameters A and C in it as well, because it depends on parameters A and C, it depends also on L. This is the Radon-Nikodym derivative that Haria and Yor also considered. So on the interval 0L, you look at this Radon-Nikodym derivative given by this expression. The normalizing constant is semi-explicit, but well, it's there. So this expression makes sense for all A and C. And one can expect that perhaps this describes the stationary measure of KPZ equation for all the possible boundary conditions A and C. Bryc and Ledoussal proved this for L = 1, and A and C positive. The paper which we have in with Alexey Kuznetsov, Yizao, Wang, and Jacek Wesolowski proves that for L equal 1 and A plus C positive and A bigger than -2, something like that for technical reasons, then this is the KPZ fixed point measure, but we are not working with this description. So what I want to say now is that there is an equivalent description of this process, which we worked out in a paper with Alexey Kuznetsov. I mean, it's a natural guess, but one has to check that this process of Bryc and Ledusal can be written as Yx minus Y0 as a difference of a Markov process, where Markov process Yx is really a Brownian motion of variance 1/2 with a drift and killed at exponential rate. And furthermore, conditioned to survive until time L, so that you have it. And then you have to start it from the correct initial distribution. The correct initial distribution is really e to the minus cy times the probability of survival. You may say that this is not an integrable expression, and it isn't, because y, I forgot to say this, y is in real numbers. This is not positive. But, well, if you think about what happens if y is negative, well, if y is negative, then this expression is not integrable, but then the process is killed at a huge rate, and therefore the integral happens to be correct. There is a formula for the transition kernel for the killed Brownian, for this killed process. I don't know whether you like this kind of expressions or not. It involves the Bessel K function, sometimes called McDonald's function, of imaginary index. If you try to compute this numerically, the only thing I can get is highly oscillatory integrals, and therefore it is difficult to make any conjectures or judgments about this from numerics, say. And then the probability of survival is, of course, the duped. It's a duped H transform, and it's based on this kernel. You should wonder, why am I showing you all of this when I am supposed to talk about fluctuations of ASEP? Well, I have to show you one other thing, which is again from the paper by Bryc and Ledusal. So what they did is they said, well, once you have this process for NAL, why don't we change the scale so that the process lives again on the interval 0, 1? Why don't we normalize the process by 1 over square root of L? And why don't we change the parameters now A and C so that they converge to 0, A over square root of L? And then what they did is they computed the limit of this process and wrote down the Radon-Nikodym derivative for that particular process, and it's simpler than the other one. And what they conjecture is that this should be a stationary measure of the KPZ fixed point on an interval, except that there is no KPZ fixed point on the interval theory. So it is a stationary measure of the process that nobody has yet. And with Alexey, what we worked out is the general plan in the paper with Alexey was, well, whatever one can do about process X, and we have a representation of process X as Yx minus Y0, we can ask what happens to a process Y instead. So it turns out that the process Y converges to what we call the Yx tilde, and then Yx tilde minus Yx0 is the eta process that they got. And again, there is a sort of semi-intuitive description of process Y as opposed to Radon-Nikodym derivative that perhaps people have intuition about, but I don't. So Y is the Brownian motion of variance 1/2 and with a drift and killed at 0. So conditioned to stay positive for the interval 0, 1, and of course killed at 0, but conditioned on survival for killing. And then there is the initial law, which is very similar to the other one that you saw. Now the process Y is positive. So Yx is positive, Yx minus Y0 is not. So their process here is not supported on the positive numbers, but the process Y is. So I don't know whether you want to say that this is a double limit interpretation, because process X was obtained as through Corwin-Kneezel work. Process X was obtained from asymmetric simple exclusion process from its fluctuations by taking weakly asymmetric limit. And then you take this limit and compute another limit as L goes to infinity, and you get another process. So it's sort of double limit interpretation. Now, Bryc and Ledusal expect that this process that they have here is sort of universal. That is, this is one of those, the KPZ fixed point stationary measures should be universal. So it should be a measure for stationary measures of many systems, interactive particle systems. And they express this somewhere, they predict that this is what will happen. So the next slide is sort of confirming this prediction. In other words, we worked out, as I mentioned with Yizao and Jacek, we worked out what happens if Q is fixed and AN and CN converge at a rate of 1/√n. We allow actually infinity as the value, but if we allow infinity as the value, we request still that AN goes to 1 and CN goes to 1. And then we allow the parameters B to converge to anything. I guess, I don't know what happens if they oscillate, but if they happen to both converge to -1, then we have to restrict how fast that happens. I don't know whether this is necessary or those are technical. The A plus C larger or equal 0 is something that is, I would say, more than technical, because we always need to ensure that AN times CN is less than 1. So this is sort of consistent with that assumption. And then what happens is that the fluctuations of the height function, this is the same height function that we were talking about before, as the parameters vary with the size of the system, but Q stays fixed, the stationary measure of, well, you can say that's a stationary measure of this ASEP with varying parameters, converges to the Brownian motion 1/√2 Brownian motion, plus this process eta that was on the previous slide. So what else should I say? Well, if A plus C is 0, then this process is Brownian motion with drift, and that can be seen in many ways. We allow values of parameters infinity, so this is a slightly more general process than on the previous slide. I said it's the same one, but it is the same one if A and C are finite. If A and C are infinite, then this process eta is in fact 1/√2 Brownian excursion. So we sort of recover also a limit from the first paper I talked about with Yizao from many years ago. The convergence is in D01 if A and C are positive. We didn't struggle to show what happens if A or C are infinite. So we just took an easy way out to get there. We prove convergence of finite dimensional distributions, and then when we can prove tightness, we prove tightness. When we cannot, we just leave it. So this is about everything that I wanted to say about the fluctuations. The last part is method of proof. Should I say anything about this, or we don't want to know?
Please, please go ahead and keep going. Any questions from anybody?
Yeah.
I have a question maybe before the proofs.
Good.
In this ASEP model, you have shocks, right? So you have microscopic shocks that, depending on the parameters, could be in one side or in the other, or fluctuate in the middle of the interval.
Well, this is something that we cannot touch. We assume A times C is less than 1. This is actually a fun region. I mean, I didn't say that, but we are staying away from shocks.
So you don't have a moving shock inside the interval in
No.
this regime. Okay.
Nothing about shocks. I would like to be able to say things about shocks, but I don't know what is true about shocks.
No, because I thought that this extra process was coming from the shocks, but it's not.
No, it's not.
Apparently,
No.
okay.
No, this is the fan region.
Okay. The fan region. Okay. Thank you very much.
Sure. So this is the reason for this technical restriction A times C less than 1, or this is the reason that we cannot access shocks. That is, all the proofs are based on a version of matrix Derrida, so Derrida, Evans, Hakim, and Pasquier, a version of matrix method. What we extracted from this method is the formula for the generating function, probability generating function of a stationary measure for fixed n. And this is the integration with respect to the stationary measure. And of course, what I am talking about for n equal 2 is, this is what I'm talking about. It's an expression for probabilities with coefficients t1, t2, and t1 times t2. And what you have on the right-hand side is an integral, multivariate integral, from the, if you are lucky, then the integral is over the interval, over the cube minus 1, 1. And there is a joint density often for those random variables. And yt is actually, I didn't use the word Markov, forgot to use the word Markov. Yt is actually a Markov process. So you have transition probabilities and initial distribution to work with. And essentially, you replace everything by the integral. The caveat is that in order to do that, you have to assume that t's are ordered. So you cannot just take t1 1 and t2 something and t3 1 again. So unfortunately, you have to have them ordered. And an illustration why you need to have them ordered is here. That is, this is the expression for n equal 2. And of course, if you look at this t1, you have t1 in the answer. You have a constant, you have a t1, you have t1 times t2. But you also have this integral of expected value of yt1, yt2. If, at least for some choices of parameters, the mean of yt is 0, and the covariance of yt, of square root of t times yt, happens to be minimum of t1, t2. So in other words, those two expressions cannot be equal in general because one of them has minimum of t1 and t2. But they are equal if t1s and t2s are ordered. So this is the result that builds on the Derrida, Evans, Hakim, and Pasquier matrix method. The second ingredient is Uchiyama, Sasamoto, Wadati paper, which gives connection between the matrix method of and the Askew-Wilson polynomials. That is, their sort of one message from that paper is that if you want to find general matrices D and E, you should be working with Jacobi matrices for Askew-Wilson polynomials. And they also extract various integral formulas, for example, for the partition function, in terms of the complex contour integrals that involve the Askew-Wilson weight. Now, of course, the ingredient, big ingredient is Askew-Wilson measure, that is Askew-Wilson orthogonal polynomials and their orthogonality measure. This is a paper that has, every time I look at it, I find something else that I didn't know. So it has lots of things. And there is another ingredient is a paper with Jacek that we wrote down for completely different motivation. We had some motivation, which I shouldn't say why. We wanted to use the orthogonality measures of Askew-Wilson polynomials to construct Markov processes. So we sort of came up with some sort of scheme that allowed us to do this. And then when we looked at the complex integrals in Uchiyama, Sasamoto, Wadati, and we looked at our integrals in our paper, well, we said, wow, this looks very similar. And that's where this result came from connecting all the dots. So I'm sort of out of time, so maybe I should say just one thing. So this is the result that I copied from the previous slide. And let's just spend a minute looking at the height function. The height function is that I wrote here differs by a factor of 2. So I slightly changed the definition. Sorry about that. But what would happen if you wanted to compute the Laplace transform of this one random variable, just univariate Laplace transform? Well, what would you do? You would take the t's to be, you would take the same value of t for 1, 2, up to nx, And then the rest of them you would take 1. So that's what you do. You take t's to be equal to e to the minus s over square root of n, and then take them 1, and then put all of those things into the right-hand side. And the height function has this minus 1/2, and that actually cancels out this term here. And what you get is you get a bivariate integral for the Laplace transform of univariate law. You get a bivariate integral, which involves partly the process, Markov process at time 1 raised to some power, n minus nx, and then Markov process a little bit earlier than 1 raised to power nx, plus the hyperbolic cosine. Hyperbolic cosine cancels those terms 1 plus t and the cancellation. So the hyperbolic cosine raised to power nx, that's what gives you the Brownian motion in the limit. And the Markov process is something that you have to work with, and basically to find the asymptotics of the univariate height function, what you need to do is you need to look at Markov process near point 1 and see how those things look like. So this is involves the expansions. Essentially, you convert the proof of the convergence of the height function to analysis of the Markov process near a single point. And maybe this is the moment that I will stop. I have a couple more slides that I think I don't want to tell you about. Yeah, I think that I will just skip that. And I will say thank you very much. This is, sorry, I'm 2 minutes over time, but that's maybe acceptable.
Thanks very much, Wlodek. There be any questions? More questions for Wlodek?
Yeah, I have a question.
Please.
Thanks for your talk. I really enjoy it, and I really find very interesting all these exact computations somehow that you were able to do. Let's focus on the case of the weakly asymmetric case, when Q and also your parameters are close to 1 plus minus something divided by square root of n. Okay, so I understand that your proofs only work with a plus c smaller than 0, right?
Well, I mean, we put a minus in 1 minus, and therefore it's a plus c bigger than 0. But yes.
Okay.
But that's we struggled which way to denote.
Yeah. Don't worry. I mean, probably it is true that each time we mention the sign, there is 1/2 probability chance of getting it wrong, right?
Yeah.
And okay, your series don't converge and etc. But this never prevent physicists to try to do computation. So should it be possible to kind of go to the other region by some sort of analytical continuation of your final formulas, or doing some resummation of these products or something like that?
Yeah, of course. I mean, if you have the function, this is what we have is a polynomial in T1, T2, Tn. So if you have the polynomial on the cone, then you have it everywhere. So that's analytic continuation, if you want to say it this way. Jokes aside, I did this calculation for very special choice of parameters where Q was 0 and square root of TYT was what people call the free Brownian motion, or the Markov version of the free Brownian motion. And I did this kind of calculations to see what would so I can write down the formulas, but I couldn't see anything from those formulas in this special case. I mean, it is perhaps the most technical restriction that, but then perhaps the phenomena are also different. I don't know whether you believe that the phenomena are the same or not. I mean, if you go from the outside, because if you go on the, I think that's the coexistence line or something, that's where the most shocks happen, then, you know, how would you know that the limit will be, you know, nice? But, yeah. I'm not saying it is not nice. I'm just saying we don't have access below above the line AC equals 1, but lots of interesting phenomena are there. The matrix method fails occasionally. I forgot to say this. Like there is an interesting case that, oh, maybe I should say that as well. So firstly, if you take a parabola AC equals Q to the N, then you can write down explicitly the distribution, the stationary distribution, and you are in this region that we cannot reach. So you can get some information about what's going on by looking at cases like this. The second thing that I think, I don't know if I want to say it, but the matrix method does not work always. Where do I have it? Here, maybe. So, you know, it is extremely easy to compute the invariant distribution when you put beta and delta equals 0. Because those particles have nowhere to go, they have to come back to return. And it is a Bernoulli product of Bernoulli measures, is a stationary measure. For every n, you compute this. Now, what happens if beta and delta are 0? Well, in the matrix method, you get V equals 0. In other words, matrix method clearly doesn't work in this case. And people know other cases where matrix method doesn't work. So our method is based on Derrida's matrix method. So if matrix method doesn't work everywhere, then our method can't work everywhere either.
Okay. So now another related question is, so this is still very preliminary, but I think that we are able to show something of the sort of that the invariant measure of the ASEP in this weakly asymmetric regime is absolutely continuous with respect to the Brownian motion. So something that you mentioned somewhere, no? That yeah, for example, in this
more measure theory than me, but you know, we have a sum of two processes, Brownian motion plus another process, and this other process is absolutely continuous with respect to the independent copy of the Brownian motion.
Yeah, yeah. So that means that you can take the sum of these two Brownian motions.
Yeah,
and I think it's going to be absolutely continuous with respect to
that sum. Yeah, and you can write down the density probably. Yeah.
So, right. But so in a preliminary computation, it seems that for all choices of parameters, even for A plus C smaller than 0, you still have that property.
So Baraquand and Ledusal seem to be conjecturing that this is the invariant measure for all of them, for all the choices of parameters. In other words, the proof works only for A and C positive, and now with our contribution, it works for A bigger than -2 or C bigger than -2. But that's technicality. That's because when Corwin, there is a technical thing in Corwin-Kniesel where they assume that some process is on the interval 0, 2, and that's where the -2 comes from. The process actually is well defined on -infinity, infinity. But the proof that they do is only on 0, 2, so I cannot claim that I could do the rest of their proof on the everywhere.
Yeah, I mean, I'm not surprised by that, because in our preliminary computations, although we can do some cases A plus C is smaller than 0, we do have a restriction on the absolute value of A and C.
Absolute value of?
Our computation only works for absolute value of A and C small enough.
Oh. So, we are way.
I mean, and it's probably related to these facts that you at some point you need some series to converge, no?
So, as I say, our representation was different. Our representation of the process was yx minus y0.
Mm-hmm.
And this representation used like this formula 3. In formula 3, in order to have the normalizing constant finite, you have to have A plus C larger than 0. Now, we did compute somewhere else what happens if A plus C is epsilon. What happens to this process Yx? And what happens to Yx minus Y0 converges, because that's the same process that you have in Formula 2 and converges to Brownian motion with a drift. But what happens to process Yx itself? Well, Y0 is not tight. Y0, we have to scale by something to get convergence to exponential. So it converges with the correct scaling, but like if A plus C is epsilon, I forget whether you multiply. Yeah, you multiply by maybe epsilon or square root of epsilon times Y0, and that converges to exponential. It's a nice limit, but useless limit.
Okay, well, I think that I already took too much time, so thanks for your answer.
Thank you.
Wlodek, I have a quick question. So the independence you prove by just factoring at the end? Is that,
sorry, what do you mean by independence?
So the limit is Brownian motion plus x.
That is actually essentially in Corwin-Knyzeł. That is, they write down the Laplace transform and it has the Brownian part plus a thing that they couldn't recognize. Now, this does not prove that the process factors like this, because you can have a Laplace transform that happens to have Gaussian part plus something, but the something might have no Laplace transform. So technically, but it turns out that it has, and therefore this is so this is actually I don't know whether that's the cosine. So the method of proof of Corwin and Knyzeł is also based on this representation that I mentioned with Jacek Wesolowski. And in that representation, cosine is always there, and the cosine, hyperbolic cosine by itself would converge to normal. So that's sort of, you have this, I mean, they are not factored there, but asymptotically they factor, and in the limit you get Laplace transform of Brownian motion plus Laplace transform times Laplace transform of something else. And this something else is where the struggle was. And that's the other two papers that are in the slide. So
is there a, I'm kind of maybe a naive question. So how do you interpret this X in terms of the dynamics? I don't know if that's a good question. But.
It is a good question. It is an impossible to answer question. What the process X should satisfy, for example, is that its derivative with respect to X at X equal 0 should be C, and at X equal L or 1 should be minus A. But of course, the process is not differentiable. So what am I talking about?
So this is some disturbance, right? Because it's adding to the Brownian motion. So
one can say, what is the expected value of this process? It is a disturbance, but what is the expected value of XX? And it's the expected value that should be smooth and have the derivative, this or that at various points. But how would you compute the expected value if you multiply this? How would you compute the expected value? So there are papers about computing expected values of integrals like 1 by Haria, Yor, and Donati Martin, but they cannot put XX. They cannot put an X in it, or there is no formulas for X. Why is it like this? I don't know. Milton might know more. I mean,
not really. It's also a mystery to me. I mean,
are we still recording?
I think so. Yes.
I can say different things when they are not recording.
Are there other questions from the audience? Okay, so why don't we thank Wlodek again, and So this is, so I was asked to mention that this is the last seminar for the year, and we'll restart August 17th. So we'll have a month or so off. So see you all in mid-August.
See you.
Thank you, Wlodek, for the nice talk.
Yeah, thank you.
Thank you, Wlodek. Thank you very much.
Thank you.
Bye-bye.
Bye-bye.